the first exercise for today is we're going to look at what are we looking at? What if we want to sort of filter out the students that are failing? Okay, so we've got this vector of students that we're going to be computing grades for. But for whatever reasons, what if we wanted to see, like, okay, these are going to fail. We want to know which ones are failing, but then also get a list of the students that are not failing, okay, that are passing. And we want to sort of separate out this vector into two different vectors. How would we go about doing that? Okay. Whenever you're thinking about a problem like this, maybe the first thing to do is not try to get too into the details of like exactly the mechanics of it, but what's sort of the overall strategy that you might want to use. So let's kind of think about, you've got this vector of students, coming in, right? You've got like student 1, student 2, student 3, student 4. And at the end of the day, we want to end up with two containers. Maybe, student 1 and student 3 are passing, and then the failing ones are, student 2 and student 4. Of course, if half the students in a class fail, the professor might be doing something wrong in that course, right? but let's think a little bit about sort of, algorithmically, how might we go from, having one vector to having two vectors. And by the way, we're going to think about a failing grade as anything lower than like a 60.
If your course grade is like lower than a 60, then put them in a new string or a new matrix or whatever.
So you're thinking you're going to sort of go through all of this, the student vector, and for each one, look at that grade and be like, okay, if it's lower than 60, sort of put it over here into this fail vector or something.
Yeah.
Right. Great. And then maybe if they're not failing, then maybe we want to put them over into this pass vector.
Yeah.
Great. Yeah, so that's a really good first shot. So let's go ahead and sort of look into that a little bit more detail, that approach. Okay, so this will be our first try up here. We'll see in a minute. It's a good idea when you're kind of looking at problems like this to go ahead and brainstorm and try out different solutions. We'll worry in a bit later whether this is the right solution or the best solution or not. So the idea here is we're going to extract out the failing students. And so here is our pass and our fail vectors that we're creating. Okay, so those are the, over on the picture here, those were the two new vectors. And then here's a loop to go ahead and go through all of those students and figure out whether they should be put into the failing vector or the passing vector. Okay? And something important to note here is we're using the pushback method. So what that does is, let's say at the beginning of time, our pass vector is going to look kind of like this. It's a zero length vector initially. And then the first thing we're going to do, suppose that, S1 passed. So when we do a push back, then this little guy here is going to transition and become, a guy with just one element in it. And that's what pushback will sort of carry out. It's an in-place update that causes the vector to grow with one new element at the very end. Okay. Of course, when you've got an empty vector, you sort of can't tell the difference between push front and push back. You can do both. But let's say we then did another push back with S3, then that's going to transition this guy to look like this one here. So after another pushback of S3, that'll be at the end. Okay? All right. The other thing to note is that, again, we're using the bracket notation here to select out a student at a particular index. So we're looking into a vector, pulling out an element at an index. It's 0 based, right? So the 0, our loop here starting at 0, that'll give us the first student, and we're going to iterate, until we hit the the end of the student vector. Okay. The other thing to note here is we've got this failing grade function, which is implemented up here. It's a really simple thing. Does just what you'd expect. We're just saying, okay, we get in the student info record, or structure, I should say, and we're just checking to see if the grade is less than 60. Right? And we already, last time we implemented that grade function. Okay, so that's sort of a complete implementation of that idea. Let's maybe any questions about how that worked, or any of the pieces of that solution unfamiliar, or does it seem pretty straightforward? Question?
No, so I was just wondering if this pushback is of which library?
Yes. So the thing to notice, so you see this dot operator?
Yeah.
So that means this is a method that's attached to the object, right? So it's this fail object that has that method on it. So then, and you might be thinking, well, where can I find the documentation for this method, right? So whenever you're calling a method on an object, the thing to do is figure out what's the type of that object, okay? And in this case, my IDE here, Eclipse, I've got it hovering over that variable, right, fail. And so, in fact, it's showing me where it's declared, where that variable's declared. And the declaration has the type there, so it's vector, right? So if I wanted to, find out about pushback, let's see here, I could grab, browser. Pull browser over here and type in something like C++ vector push back. And you might be wondering things like, sort of, what's the time complexity of pushback? How long does it take to add something to the end of a vector, right? So here we might, look at what's going on. There's, you might cause a reallocation of the internal storage, which is rather expensive. Unfortunately, this documentation doesn't actually say, oh, wait a minute, here we go. Here's the complexity. It says it's constant time, but then it's which means that it's sort of like a small fixed amount of time per call. But then it has this comment here that sort of says, well, that's sort of true, okay? So if a reallocation happens, if it needs to grow the amount of space for that vector, that's costly. But what it's not saying here is that it'll actually sort of double the size of the vector. It's going to grow it more than it needs to, because that way the next time you push back, it's going to really be constant time. And so you're going to get a whole bunch of pushbacks before you have to reallocate again. So that's, by amortized, it means that one big cost of reallocation is actually, you're kind of paying for it a little bit, theoretically, for every pushback. And so if you do like 1 million pushbacks, it's going to feel like constant time after having done 1 million pushbacks, even though some pushbacks are going to be really fast and some are going to be slow. Okay? Alrighty, let's move that back out of the way. Good question. All right, so now let's think of a little bit, now that we're sort of talking about time complexity, let's think about the time complexity of this program, or also the space complexity. Right? One thing to realize here is that we're creating these two completely new vectors. And so we're going to be, and at the end of the day, all of our students are going to end up in those two vectors. So we're going to use like, essentially, we're going to still have the existing data there, the student vector, and then we're going to have basically a complete copy of it. So we're going to need sort of twice as much space as we needed to begin with. Okay. Now, for most purposes, this might be fine. You might have, disks are cheap. Memory is cheap. But who knows? Maybe you're at Stanford teaching one of these giant online courses with 100,000 students. Keep going back to that example. And so maybe that's a problem now. Maybe you don't have enough memory for that. Okay. So let's maybe think about another solution that doesn't need as much memory. And suppose, let's think of a case where maybe the number of failing students is fairly low. So we're not worried about sort of having a failing student vector, but maybe we don't want to, sort of have that duplication of having the old data there still. Okay. So, or maybe another way to put this is instead of trying to take the old vector and turn it into these, and then have two new vectors in addition to the old one, maybe what we'd like to do is end up in a situation where we only have the pass and the fail vectors, and we sort of reuse the old vector to be maybe the pass vector. Okay, so our original vector maybe gets shrunk into just sort of having the passes in it, and then we have a new guy with the fails. Okay, so this one's new, and then this one's the old one that has the passing students. Okay, so if we do it this way, we won't need any, the amount of space we'll need is going to remain sort of the same as what we at the beginning of the program, right? We're going to have this student vector, and we're going to be shrinking that vector and increasing the size of the fail vector. So we're not inducing any new space overhead. Okay, so let's see how we could do that. Here's sort of a first attempt at this. So we've got our student vector coming in, and here's just our one new vector for fail. It's currently empty. And then the idea here is that if you've got a failing grade, go ahead and push it back onto the fail vector. But then we also need to erase the failing guy from our existing students vector that's sort of becoming just the passes. Okay. Now this expression to the right here takes a little bit of explaining, and maybe also let's explain a little bit about what erase does. Okay, let's go over to a picture here. Let's do it new. So we have our original vector, and suppose 2, 3, 4. Suppose we're going along, and let's say this guy. Let's say the first one is passing, but the second one's a failing guy. The erase method is expecting to be given an iterator pointing to the spot that you want to erase. Okay. Now, if you remember an iterator, just think of it as like a cursor of some sort. It's something, kind of like pointing a finger or something that's saying, "Hey, I care about this position in the container, in the vector." Okay. So if I have an iterator pointing there, I could then, let's call it iter. I can say, and this is ours. Let's call that whole thing S. I can say s.erase iter, and that'll do the right job. Okay. Now the next question, of course, is, well, how do you obtain an iterator pointing at the right spot? Okay. Well, we know we can use the begin function which will give us an iterator pointing right there. Or we can use a .end function, which gives an iterator pointing sort of one past the end. Okay. We can also move iterators around using operators like ++, which sort of kind of does what you might think it does. You know, you've seen what it does for integers. For iterators, it moves it to the right by 1. Minus moves it to the left. You can also do addition. So for example, you could say s.begin +1. Okay, and that will move, or will create a, it creates a new iterator that's pointing, 1 over. Okay, so in fact, this is the kind of expression we want to do to get, we get the beginning and then move it over by 1 to get it pointing at the spot that we want. All right. So in general, kind of moving back over here, the spot that we care about is I. So we can say begin plus I to get to the spot that we care about. Okay? And we do an erase. All right, so what does the erase really do? So under the hood, what's happening, so if you think of sort of a snapshot here, after the erase, the vector is going to look like this. Okay, and you'll see that it's shifted everything down by 1 slot. Now, how does it do that shifting? It's copying. So it's copying S3 from where it was to the new place, and S4 from the old place to the new place. And then you might ask, well, what happens to the this old spot here? In some sense, the memory is still sitting there. That's sort of dedicated to this vector, but the object that's there has been destroyed. Okay, so it's sort of now back to being sort of raw memory that isn't dedicated to an object anymore. Okay, and if you ask this vector what's its size, it's going to say my size is 3. Okay, so it's the size is shrunk by 1. Okay, so the cost of, or maybe I'll ask you, what's the cost, sort of in general, of this erase operator? In terms of the length of the vector, or what's the worst case sort of cost?
Looks like it's probably linear.
Looks like it's linear, that's right. So the worst case is you're like erasing the one right at the beginning. And if there's n elements in the vector, you're doing n copies to move everything down by 1, right? So that's a fairly hefty cost. Okay. Yeah.
Is there a difference between if you ask the vector how long it is versus how much memory is allocated to it? Is there a difference?
There is a difference. Yes. If you say give me the size, right? S.size here, that gives you the actual number of elements, objects that are allocated in your vector. If you say S.capacity, that will tell you how much actually memory has been dedicated to the vector. Okay.
So will erase decreases the size, but it won't decrease the capacity?
It doesn't necessarily decrease the capacity. I'd have to double check, but I think it's not. It doesn't. It's not. It's free to decrease the capacity if it wants to. For example, like let's say the number of elements got to be much less than half of the capacity or something, then it might decide to go ahead and do a reallocation. Cool. All right, so then if we look at this code and think about the overall time complexity, okay, we've got this erase operation here that's a linear kind of thing. And then that's nested inside of a loop that's also going over all the students. So that's also linear. Okay? And when you have nested like that, what we're looking at now is so n times n, or n squared in terms of the time complexity. N squared is quite a big difference from just O of n, right? This is That's why up here I'm saying this is not really time efficient. And you want to be cognizant of these kinds of changes to your programs. I mean, especially if you care about scalability or things like that, that all of a sudden you've gone from an O of n kind of thing to n squared. Okay? So now, maybe the next step is to think about, well, what can we do to still sort of have this behavior where we want to keep the amount of space we don't want to have to grow the amount of space to do this operation. But we also want it to be efficient. We want to be able to do this in sort of a linear amount of time. This next step is going to be a little bit of out of the box, thinking out of the box in some sense. So if you've had a data structures course, you might have that's one hint as to what you might be thinking about in terms of what to do instead.
I feel like it might have something to do with an in-place sort,
In-place sort.
but I can't remember what the algorithm is for that. Or what the complexity.
Not completely obvious to me how that would get rid of the problem. Yeah, maybe some kind of in place sort of, you might, maybe are you thinking something along the lines of, instead of doing an erase and shifting everything over right away, maybe you could sort of like lazily shift things over.
Or like replace, do some kind of replacing, because doesn't like quicksort do something like that? I can't.
Well, quicksort, you're not actually trying to erase any elements out, right?
But if you sort them so that one block is all fails and one block is all passes, then you could just change your pointers around and do some tricky stuff like that.
Yeah.
But I don't know what the time complexity of that would be.
That's n log n, I mean, so what you're basically saying is you could sort where the criteria for your sorting is whether you're passing and failing, right? And that would do the trick. In fact, we could even just call the sort function with, a slightly modified version of this, failing grade, In fact, that would work. You could just use this. Well, you have to think about it a little bit. What you want to do is if a guy that's passing, so you're going to have to take two student names or two students and then say, if one guy's passing, the other guy's failing, then consider the passing guy as being greater than, something like that. But that would be O of n log n, and maybe we could do even better than that. So we'll kind of give it away here. With data structures, vectors are sort of, famous for being, you can access the middle of a vector really fast. You can just say, give me the ith element, and you can push things on the back. But erasing stuff from the middle of a vector, sort of like, it's just not good at that, right? We've seen that that's sort of a costly operation. But there's other data structures that are good at being able to delete from the middle. Okay, and the linked list is an example of one of those data structures. Okay, so kind of what's going on here is you want to pick a data structure that matches what you want to do with it. Okay, so let me kind of draw what a linked list would look like. Here I'm sort of looking under the hood at how it's implemented. Okay, so you'd have your S1, S2, S3, and S4. And then inside the linked list, the way you know what's the next student is you've got these pointers going back and forth. And let's say I want to delete S2, then all I need to do is to reroute the pointers. I just need let's go ahead and delete these pointers here. And then I just have to reroute these guys to bypass, right, that one element. Okay, so that's a fairly fast operation. Okay. So kind of now, fortunately, the C++ standard library has linked lists already for you. So, you don't have to go and implement all the fun details of getting the pointers right, going back and forth. We can just switch over to using a linked list, and then all of a sudden things are going to be a lot faster. Okay, so let's go ahead and switch over here. Okay, so what I've done here is instead of vector now, I've swapped in a list, both as the input and as the output parameter. Okay. Oops. And then as you look through, I've turned this failure container into a list. Okay. Now, previously when we had that for loop, we were using sort of this index I to sort of access elements out of that vector. Well, you don't want to do that in a linked list. Okay, you don't want to ask for the ith element of a linked list. So, because what does that mean? Let's say I want the thing at position 2, right? This is position 0, 1, 2, and 3. If I were to say, give me the thing at position 2, well, using the original sort of setup, I'd have to sort of follow 2 links to get there. And again, this is going to be a linear process of following the links, right? So that's super slow, right? But then we can think to ourselves, well, do we really care about accessing the ith thing, or is there some better way to keep track of where we are? Okay, and so that's where the notion of iterators comes up again. Okay, so what we're going to do is we're going to maintain an iterator that's pointing at where we're currently at in processing our students. And then we're just going to keep moving our iterator along as we sort of process the students, okay? So let's see how that works. Okay. So here's the first line where we're saying, okay, I want an iterator that's pointing to the beginning of my students list, okay? Now, to declare this vector, we need its type. Now, this big thing over here, kind of a mouthful, is how we get the type of that iterator. It turns out this type has been defined inside of the list class. Okay, and so we can just say list, of student info, and then : means, remember, reach inside, and then we're going to get out the iterator type that's inside of that list class. Okay. Now it turns out that inside that list class, this iterator type is, it could be referring to some other class called like list iterator or something like that. We don't really know what it's called under the hood, but this is sort of the list class's way of publicizing to us what the right type is, whatever that is. Okay. And we don't really care what it is as long as it supports all the iterator operations, which indeed it does. Okay. So one of the things that we can do with iterators is we can compare it with other iterators. And in this case, we're going to be comparing it to the end. Okay, so that's how we'll know when we're done, is when the current iterator, our position, is pointing past the end of the students. Okay. The other important operation that we can do in an iterator is called dereferencing, which is just putting an asterisk or star in front of the iterator. That's saying, give me the thing that you're currently pointing to. Okay. So suppose our iterator, we've just said, students dot begin. That at that point, iter is going to be kind of represented by this arrow here that's pointing at the very first student. So then if you say, iter star, then that's going to give us S1. Okay, so that produces the S1 student. Okay. Right. We have that student S1. We then, want to ask, is it a failing grade or not? Right. if it is indeed a failing grade, then we need to go ahead and put that student into the fail list. And then we also want to erase that student from the current list. Okay. And here again, we pass in the iterator. Now, for the same reason that you can't, that it's slow to ask for the like ith position in a linked list, it would be also slow to sort of do things like plus operators on a list iterator. In fact, you're not even allowed to do a plus operator on a linked list. Okay, because what that would do is that would basically give you the ability to sort of jump forward, an arbitrary distance in your list, which is going to be slow. So there's sort of like whoever did, Alex Stepanoff, who designed this library, sort of didn't want to give you ways of shooting yourself in the foot. So he just said, no, we're not going to give you the capability with lists to jump forward. Okay, but we don't even, in this situation, we don't even need it, right? We've already got this iterator that's pointing at the right student. And so we can just say, okay, go ahead and erase using this iterator. Okay? And if, alternatively, if that student is passing, we just leave it there and we increment the iterator to point at the next student, to point at S1. Okay? So then at the end of the loop, by that time, our students list has become just the passing students, and then we return the fail list in addition. All right, so this was a fair bit happening in this example, right? So we're switching from vectors to lists, and we're getting to know this concept of iterators. Okay. Probably a good moment to pause and take questions. So did you have a question?
No.
No?
I actually got a little confused between how you're getting failing grade star iter.
Failing grade star iter.
I mean, what does that mean?
What does that do? So whenever you see sort of a complex expression like this, you want to break it down into parts. So there's sort of two parts to it. One is just the star iter part, and then the call to failing grade is sort of the second part, right? And so that first part, that's kind of what I was trying to explain over here with this. So we've got this expression star iter. Okay. Now at that, well, let's say this is the first time through the loop, right? So what we initialized iter to was the beginning, right? So at the very beginning, star iter, you can think of iter as being this pointer here to the very first student. Okay. So star gives you what's stored at that position. Okay.
Yeah.
In this case, it's the student S1, right?
And
Now,
failing is just a function which you have defined.
that's right. Yeah. So the failing grade, that was up here.
Okay.
And we were still calling failing grade like in the previous example, but the way we were getting the student was different, right? But then let's go all the way up here, and here's the actual failing grade function, right? That just says, okay, give me a student, and I'll compute the grade and check if it's less than 60.
Okay.
Yeah, bunch of moving parts with these examples, so it's gotta, just take it one little piece at a time. Now the key thing that's happening here is this erase on the linked list. Okay, erase on the vector was a linear operation, but now erase is just a constant time operation, and now we can kind of go through, all of the things inside of this loop here, all the operations, and be like, yeah, each of these operations is constant time with respect to the number of students. And so we end up with the loop overall is now just a linear time kind of thing. Here's a question. Was it important for us to change the fail from being a vector to being a list? Was that an important change or not?
No.
Yeah, you're right. It wasn't important. We could have left it as vector, and that would have been fine. Okay. Any other questions about sort of the using these iterators to manipulate containers? One thing I should point out is that there's a lot of different kinds of containers in the standard library. There's vectors, there's list, there's things called sets and maps, and so on and so forth. They all support iterators and this begin-end kind of thing. And so in some sense, it's a better style of programming to program it in sort of the style that we have here using the iterators. Because let's say later on I figure out that maybe list isn't as good as something else. I can fairly easily change this code to use a different data structure and still use the iterators. Okay, so once you've got something in iterator style, then it's easier to switch out to different container types. So if I wanted to change this to use vectors, I could just I just have to change this part here, this part here, and so on, and the rest of the code works just fine. Okay. Now, if you wanted to go even further in terms of making this extract fails function easy to use with different container types, you could turn extract fails into a template. Okay, so we're not going to talk about templates today, but just sort of some sort of foreshadowing in terms of things to learn about is that if we turn this into a template, we'd actually parameterize it with respect to what kind of container it's using, and then we could use it with with all kinds of containers, and it would work out fine. All right, let's look at changing the code, the rest of the program, to use this. So first we want to think about, if you remember right, we sort the students and then print out their grades. Maybe, just for simplicity, maybe we want to do the extract fail here, for example. And for the moment, let's say I just want to forget about the failing students, but later on you might want to go back and send those somewhere. Okay. Of course, there's a little bit of a bug here. Oh, wait a minute, it just doesn't even know what extract fail looks like. There's an S. Okay. But there's still a problem. Candidates are, so first of all, candidates, it's sort of looking for candidate functions to call. And it knows that there's a candidate that takes a list, okay, std list, but we're passing in a vector, so that's why it's complaining, is there's a mismatch here. One thing to note too, let me hover over that again. You're seeing std list, student info, and then there's this allocator thing. Okay, it turns out the list class takes 2 template parameters, and this second one has a default, and so you normally don't care about it at all. Okay, but when you're looking at error messages like this, it sort of shows you all the information. And so the main thing to know at this point is just to sort of ignore that allocator parameter. Okay, right. So the idea here is that, oh no, we need to sort of change this guy into being a list. So maybe we just want to do this. Okay. Okay. Now, let's save that. Now let's see an even worse error message. I'm going to build a project. Whoa! Do you see this error message flying by? This is another one of these error messages that my thesis work was set out to fix. Okay. So there's a warning here that we don't really need to worry about. But here, it's saying, hey, somewhere on Earth you're using operator bracket. And then if you look a little bit further down, it says, here's, this is somewhere in the C++ standard library. And it's talking about the sort function. Okay. And it's complaining about this inside of the sort function. So when you see one of these sort of incomprehensible error messages arising from the standard library, it probably means that you've made a mistake in how you're using a function. And in this case, it's how we're using the sort function. Okay? Now, it turns out that the sort function is really expecting iterators that can jump around, like the ones you get from vectors. Okay? Because it's using quicksort or a variation on quicksort. So we can't use, but with a linked list, we can't use this. So it turns out that there is an alternative sort function, or I should say sort method, on the list class that we can use instead. There's also alternative sorting functions in the standard library that we could use, like a merge sort or something like that would be an alternative approach. Okay. So that got rid of that error. But now there's some more errors down here. Let's look at this loop. So here's a little bit of a quiz. What's wrong with what we're doing here? And it has nothing to do with the set W stuff. Just changed from a vector to a list. There are certain operations that are good for vectors, but not for lists. Do you have a guess?
The dot operator?
So the dot operator, so by that time we've got a student record, and we're sort of asking for the name of a student, which is fine. So not quite, so that's fine. Oh, the only thing left is the bracket operator, right?
Yeah. Should be star?
Well, so the issue here, it's more than just that we need to be iterating, or we need to be dereferencing something. We need to be working with an iterator so that we can kind of be marching through this thing and be able to get at the current element, instead of saying, oh, we're just going to jump every time through the loop, we're going to keep jumping to different parts. Okay? So we need to get rid of this whole int I, thing. And instead we need to be working with list iterators. So here I've just said, okay, now I'm switching over to a loop that's iterator-based instead of index-based. Okay? And whenever you're sort of iterating over a container like this, this is a very idiomatic style that I just wrote this for loop in. You basically want to use exactly the same sort of style to write your loops. If you follow the style exactly, they'll just sort of always work and you don't have to think about it. If you start playing around with maybe you might be tempted to use a different operator here, like less than, you can get into trouble. So like less than is something that is an operator that's available for vector iterators, but not list iterators. Again, because it would actually be slow on a list iterator to figure that out. So you want to stick with less than. The plus I here, this is...
Plus iteration.
Oh, this should be iter. Thank you. Right, that's moving the iter to the next spot. And that's sort of the best idiomatic way of doing that. Right. Okay, so now we want to get rid of this expression and just put star iter. that does that job. We need to, do we see any other places that we need? Oh, down here as well. And that does it. Okay, that's just an old error. Let's try to build this guy now. Good. I think there are some warnings, but nothing serious. Okay. Maybe one other little tidbit. Whenever you see a star and a dot kind of being used in combination, there's a shorthand that you can use instead. Okay, and that's sort of this arrow notation. So I'm going to get rid of the star and the dot and just do an arrow. It's just that this dot, the star dot sort of combination is so common that Strustrip decided to make a abbreviation for it, and that's the arrow, the arrow operator. Any questions about that final changes we made? Yeah, so I would encourage you to go ahead and kind of get used to using iterators. That's sort of the accepted, sort of encouraged style to use in your sort of modern C++ code. And you're more likely to end up with code that's efficient and that's sort of more portable and things like that if you use iterators. And it's sort of more amenable to using the standard algorithms. So all the standard algorithms like sort work in terms of iterators. That's sort of the currency that they work in. So if you're already sort of used to using iterators, then it becomes fairly natural to make use of those standard algorithms. Okay. All right. So there's a couple things from. So this was the chapter about using containers and analyzing strings from the book, Accelerated C++. There's a couple more things that were in that chapter that we didn't get to. One is, in the two parts, the rest of the chapter is all about sort of manipulating strings. So one of the things that we do is, learn how to split up a string based on white space into the individual words. And so there's sort of an algorithm that sort of that it walks you through in terms of figuring out how to iterate through a string and chunking it up. And it basically it shows using a string just like a vector. You can use the bracket operator on a string and sort of look at each character and find the ones that are the white space characters and break them up like that. And then the second example is you're working with ASCII art again. So how we did those triangles and things with the asterisks. Well, the idea is that you've got these sort of squares of characters, and you're storing them using a vector of strings. So you've got a vector that has each row, and then you've got a string sort of that for each of those rows. And then there's kind of fun operators that you can do with these blocks. Like one of them is put a frame around a block to create a slightly bigger block. It also has operators like if you take two blocks and you want to compose them sort of horizontally, you can sort of stick them together. So there's this function that it goes through that says, okay, here's how you take two of these things and put them into one big block. And there's also one that does vertical sort of composition where you can take two blocks and stick them together. And then you can imagine that if you had maybe, I don't know, a sequence of ASCII pictures that you wanted to put together in a cartoon or something, then you can sort of compose these together using the sort of the vertical and horizontal composition. So I'd encourage you to go in and check out those examples as well. Great. So that finishes up for this time. We'll do one more lecture next week, and that'll be it for this semester. Though there's a good chance I'll do this again, possibly in the summer or next fall as well. And at that point, I'd probably pick up where we left off. Some of the upcoming chapters get pretty interesting in terms of not just using vectors and using these algorithms like sort, but then how do you actually implement classes yourself? We'd start to get into that side of things. All right. See you next time.